Can you see?
We see everything.
And it's
So
okay. I think it's
Right.
okay.
Yeah, yeah.
Okay. I think it's better. Can can you see me and hear me fine?
Yeah.
yes,
Okay, good. So
perfect.
good. This is joint work with Tom Hutchcroft, who is at or was at Caltech until just about now moved to Princeton. He was at the math department at Caltech and moved to the math department at Princeton. Olga Rospuskova is a graduate student here at Caltech in social sciences and economics. Okay, so we're going to talk about a pure coordination problem, but it's going to be played on a network. So what do I mean by pure coordination problem? It's like battle of the sexes. You just want to coordinate with the other person. There's no other kinds of incentives here. So some examples that I have is, what day of the week do we rest on? So, we can call it Saturday, Sunday. It doesn't really matter. They're all completely exchangeable. We just have to coordinate and all rest on the same one. What do we name a new concept? We want to find a word, a collection of sounds that describe something. It doesn't really matter if we call it dog or chien. It's as long as we're all using the same word. Okay, then it's fine. Which side of the pavement we walk on? So I gave this talk in Australia, and I noticed that people move to the left when you pass them on the street. Um, in this model, decisions are going to be made locally. So that's very important. We're going to have a big social network. Imagine farmers living in the Midwest, and each person has four neighbors that the neighbors in the networks are not going to be, I called it a social network, but really the neighbors in the network are people who are affected by what you do and who affect you. So maybe you know a lot of other people, but imagine that everybody has their four next door neighbors because they live on a grid. It's a very large network, and people are going to decide locally what to do. Which means that you necessarily have to have inefficiencies, because if we make a decision in some area of the network and other people make a decision in a different area of the network, and this is done locally, we can't hope to perfectly coordinate. So we're going to have some inefficiencies. We're not all going to be doing the same thing. And the question is, on which networks can we get low inefficiency, almost efficiency equilibria? So this is going to be a question about the geometry of the network. What kind of graphs, what kind of networks allow us to coordinate well locally, and what networks don't? So far, so good? Okay. So here's the model. We're going to have a finite set of agents. We're going to have a social network graph. The nodes of the graph are the agents, and they're going to be edges connecting people to their neighbors. And these edges are always symmetric bidirectional. So if I know your neighbor, you're also my neighbor. Actions are just going to be +1 or -1. We could do the same thing with more actions, but I wanted to keep it simple here. And my utility is very simple. I'm going to choose my action AI. Each one of my neighbors is going to choose their action AJ. And I get 0 if we choose the same action. I get -2, I guess, if we choose different actions. Okay, so I just want to match as many of my neighbors' actions as possible. That's my answer. We're going to have communication. So here's how it's going to work. Before choosing their actions, each agent is going to send messages. The messages are going to have to stay local. So BR of I, these are all the people whose distance on the network from me is at most R. So B1 of I is all the neighbors of agent I. B2 of I is all the neighbors of I and also their neighbors. B3 is also the neighbors, 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 and so on. And each agent I is going to send a private message, MIJ, to each other agent J that's in this R neighborhood of I. Okay, so you could have imagined a model where I want to keep it really local. I only talk to my very next door neighbors. This is somehow trying to say, look, we're going to be able to have direct communication with people who are maybe a bit further out than just my next door neighbors. But there is this parameter R which says, okay, I still want to keep it local. So I want to think of the network as much, much bigger than R. Maybe R is fairly big. Maybe it's 10 or something. I don't know. But the network should be much, much bigger. So I can't talk to everybody, but I can talk to some number of people around me. Does this make sense?
So, quick question. So, given that you're going to be sending both this sort of locally public message and these sort of private messages, I mean, I guess I'm curious why not go all the way and just let them send messages to arbitrary subsets within the ball of radius R.
Oh, yeah. So I changed. In this model that I'm presenting here, there's no public messages. I'll maybe talk about that later if if I have the time. To keep things simple, I just have a private message. I'll talk later about what happens when I can maybe only send public messages, and then you could also imagine things in between. The Barring incentives, I can in equilibrium, maybe I send the same private message to some subset, right? So in some sense, private messages are stronger than public messages because I can, if I want to send a public message, I just send the same message to everybody. There are maybe incentive issues. Maybe the public message is a sort of commitment device that I don't have when I'm sending private messages, and maybe I want to cheat and not send the same message to everybody. Does this make sense?
Yeah.
Can I just confirm R here is exogenous?
Yes. R is going to be a parameter of the model. Exactly.
Omer, can I ask a couple of questions?
Please.
So going again to the messages. So I send a message, and everybody who is in the R distance from me sees that same message. I cannot tailor messages.
No, these are private messages. So MIJ, it's a
Yeah.
private message between.
So I can only talk to people who are R away from me, but I can distinguish their messages and so on.
Correct.
Yeah.
Correct.
And secondly, these messages, and then I guess the actions, they're going to be simultaneous, are they?
The messages are simultaneous. So everybody sends a message. So they're going to be, I'll get to that, but you send a message, everybody then receives messages, and then everybody chooses action simultaneously.
Okay.
Okay. So okay, I will talk later if I have time about public messages where I just have to send, I just choose one message and it gets broadcast to everybody in my ball of radius R. But either way you do it, I want to think of this as some kind of reduced form for maybe a more intricate communication process. Maybe over time, I manage to send messages further and further away in the graph by having them pass from person to person. You'll see that for our main result, it's not really going to matter much. And in fact, our main result will apply to many models for which this model serves as a reduced form. Okay, so you want to think about this maybe as these people who are my friends. I don't really know them, but I can somehow send them a private message anyway through my friends. But okay, let's move on. So as I said before, there's 3 stages. Each person sends a private messages to each person in this R neighborhood. Everybody receives messages, and then everybody chooses an action. So this is the game, and action agents are expected utility maximizer.
So Omer, I'm sorry, but I just want to make it up because I think you already said exactly this. But so I can send a message to a friend of a friend who's not my friend privately, but my friend does not see that message.
Correct. So
I'm giving him an envelope, and he passes it on, but he doesn't open the envelope. Essentially, that's what you're assuming.
Exactly.
Okay. All right.
Yeah. So maybe you want to think of the connections in this graph as neighbors, people whose actions affect my payoff. But maybe I know more people that I can communicate with, even if they don't, if they're not my next door neighbors. Does that make sense?
Well, actually, here you can communicate with more people than the ones you have connections. Okay. We'll talk about it later.
I'm saying maybe connections.
No,
maybe a connection doesn't mean
that was my
maybe I know a lot more people than I have a connection with. What
Yeah.
the connection in the network signifies is that your actions affect my payoff, which is maybe a subset of the people that I know.
Okay. All right.
Okay.
Yeah. Okay.
Good. So here's a trivial equilibrium. Everybody plays +1. Great, problem solved. We've all coordinated, right? That's an equilibrium. You don't send messages, all the messages are trivial. Everybody just plays +1, right? So, but that's not what I'm interested in. I'm interested in figuring out how we can coordinate. So, that's just sort of sweeping the thing under the rug. Sure, it is an equilibrium. If we all decide to play +1, then we don't have a reason to deviate. But how did we coordinate? So, this is more about how can we coordinate well. So to get away from this problem, I'm going to look at equilibria that satisfy what I call action symmetry, which means that a priori, if you ask before the game starts, before any messages are sent or received, before any mixing, you ask what is the probability that an agent takes action +1, the answer should be 1/2. Okay, so the way I want to think about this is I'm interested in equilibria where a priori we're not leaning this way or that way. We're going to need to break ties somehow. And we're going to do this locally by mixing, by choosing random messages or random actions. But we're not predisposed to choosing this or that, which would sort of make this whole coordination thing trivial. So imagine again this question of choosing which day of the week to coordinate on. So you have the Mayans in America, and you have the Chinese at 1000 AD. You could say yes, they all coordinate by choosing Saturday, but how do they do that? A priori, all the options are the same. We want to think about this about the coordination is coming from somehow breaking this ties between these completely indifferent or identical and indistinguishable options. Does this make sense? So I'm not going to, I could have had a stronger requirement, which says literally agents treat +1 and -1 symmetrically. The whole equilibrium is invariant to renaming +1 to -1. I don't really need that. All I need is that the prior probability, a priori, the probability that any particular agent chooses +1 is exactly 1/2. One more caveat. All the results we'll go through, if instead of 1/2, we would have said it has to be between 0.1 and 0.9 or something like this, we would have some different constants in the results. But I just want to exclude a priori coordination on one of the actions. Okay. Good. So I'm gonna call this quantity the average expected inefficiency. So what is this? I'm looking at the probability that two neighbors, I and j, miscoordinate. And I'm multiplying it by 2 because the utility is twice the probability that or the disutility is twice the probability that miscoordinate. But then I'm dividing by the number of edges. So this is the average number of edges or the average disutility across all the edges. Up to this constant of 1/e, it's just the sum of the utilities or minus the sum of the utilities. So this is just welfare, but I'm normalizing it by the number of edges. It's sort of asking what fraction of the number of edges do we have what fraction of the number of edges do we have miscoordination? This makes sense? And if you think about it for a minute, you'll see that the inefficiency cannot be 0 when a network has radius larger than r. If we have two areas of the network that are far apart from each other, by far I mean more than, I guess, 2r apart, then the person in the middle here chooses each action with probability 1/2. The person in the middle here chooses each action with probability 1/2. And these are statistically independent. These, as random variables, these are independent, which means that the probability that they're the same is 1/2, which means that if you take a path between these people, and if they're different, there's going to be some path in the graph between these people where things switch from +1 to -1. So you're necessarily going to have positive probability of inefficiency. So you're going to have positive expected inefficiency. And the question is, on which graphs admit action symmetric equilibria that achieve low expected inefficiency. Okay. Now, when R is very small, when R is say 1, you expect very high inefficiency. And whatever the graph is, if I only communicate with my next door neighbors, I'm going to have a lot of inefficiency because anybody distance 3 for me or 4 for me is going to already be doing something that's statistically independent. But what we may expect is that when R gets bigger and bigger, if I can communicate with more people, then I can coordinate better. So maybe on some networks that are very large, when I make R larger, still smaller than the size of the network, but when I make R larger, inefficiency will get very, very small. And the question is, what are those kind of networks? On which networks can we hope to coordinate? Well, at least for large R. For small R, we can never coordinate. Any questions or thoughts about this?
Just a clarification. So here you're changing the network, but that means also you are changing the number of games or bilateral games that are being played, right? So that
Yes,
means
that's
that
why I'm taking the average along edges, right? So I want to ask, what is the fraction of edges along which I have miscoordination?
So,
So that's
but
how we can-
mechanically, by increasing the connections, the network, that will create mechanically more opportunity for miscoordination in that sense.
If I sort of hold the number of agents fixed and increase the number of edges, yes, that will create more opportunity for miscoordination. But the way I'm going to be thinking about it is, however, it's a bit different. I'm going to be thinking about all the graphs are going to have everybody's going to have some small number of neighbors. So everybody only ever has 2 or 3 or 4 neighbors or something like this. But I make the graph larger. I think of, or I change the geometry of the graph, even though the number of neighbors is fixed. So the exercise wouldn't be here about increasing the number of neighbors that each person has. It's going to be about changing the geometry.
Thank you.
Okay? Good. So here's a very bad equilibrium. We don't send any messages. We don't get any information. We don't bother coordinate. Everybody just tosses a coin and mixes half-half. Okay, so the expected inefficiency, I guess, is 1, or each edge there's a probability of 1/2 that we miscoordinate. This is very bad. This equilibrium exists on every graph, but we've totally not used our opportunity to talk about things and coordinate, right? So the point is all graphs are going to have a bad equilibrium. The question is which ones have a good equilibrium. Okay. Here's another extreme. Imagine that my graph is very small. What do I mean by small? There's some person, I'll call them a leader L, that can communicate with everybody. Everybody is a distance at most R from this leader L. And, one example is like a star graph. There's a leader L in the middle. Everybody is just neighbors with this leader, and R is 1. That would be one example. But maybe R is 10, and the graph is more complicated. It's bigger, but everybody's at most distance 10 from some person who's the leader. So then it's also very, very easy. We just have the leader send everybody the same message. The leader says, we all do +1, or we all do -1. Chooses this at random uniformly, and everybody follows the leader. This is obviously an equilibrium, and there's 0 inefficiency.
Omer, can I ask, doesn't this equilibrium in a lot of ways suffer from sort of the same problem that you were critiquing a few slides ago, right? Of like, why don't we all just play +1? And well, how do we coordinate on picking the leader? Right? It seems
Okay,
like the same
good.
problem. You just kick the
Yes.
can.
Good. Okay, excellent question. So here's a way to fix this. Imagine that let's imagine that we have a graph where everybody is of distance R from each other. So there's nobody who's sort of different. We're all distance at most 10 from each other. So anybody could be the leader. Anybody could send messages to everybody. Here's how we can solve this. Everybody picks not just a recommended action that they want everybody to take, but everybody also picks a number between 0 and 1. which they choose uniformly between 0 and 1. Everybody sends to everybody the action that they recommend that everybody do, and also this number between 0 and 1. And we go with the person whose number was highest. So, we choose the tallest person as our leader, and we do what they say. So now we've also chosen the leader through local coordination. Of course, then you can say, well, how did we coordinate on this mechanism of choosing the leader? So at some point, I'm running out of answers. But that's one thing you could do. Another thing you could do is have everybody send a recommendation and go with a majority, maybe. So at least for an odd number of people, that would work. You're always going to have a strict majority, and then you don't even need a lead.
And that sounds quite a bit more convincing to me. And even if there's an even number, if it's a large even number, it's very unlikely that you get a tie. And so it could be very inefficient in the event of a tie, but that almost never happens.
Yes. So what we'll see let's come back to this example, because the leader thing, I know how to generalize beyond these sort of trivial graphs, but the majority thing, I don't know how to do it very well locally, but maybe there is a way to do it. Okay. So let's try to take this leader idea and do it on a bigger graph where there's not one person in the middle. And here's sort of something kind of silly that you can do. I'm going to call this a leader equilibrium. I'm going to divide the set of agents into communities, C1, C2, and each community is going to have radius at most R. So what does that mean? In each community, there's a leader, a person. In C1, there's L1, whose distance from everybody in the community is at most this R. And now we just do the same thing, but within the community. So in each community, the leader is going to send a message to everybody in their community, send the same message, say do +1, and everybody just follows their leader.
Sorry, so are you claiming that you can always do this, or you're imagining a situation where that can be done?
You can always do this, I guess, because you can make the communities very, very small. You can just have the communities be singletons, for instance.
Mm-hmm.
Right? In which case, but here, all I'm saying is we somehow divide the graph into communities of radius R.
Okay, but you say it can be done. It doesn't matter the R, there's always a way to do it.
Yeah, because you could just have the partition be into singletons, for instance.
No, right? But I'm saying for a fixed R, you can always partition in communities of radius.
At most R, right? So the radius is at most R.
Okay.
Right? It doesn't have to be exactly R. So there's really nothing deep going on here. There's no combinatorial statement. It just says we somehow break it up into groups. We make sure the groups are small enough. Maybe the groups are all edges, except for some that are singletons. That's another way you could do it. But we somehow break this graph into these communities. Each community is small enough to have a leader, and then the leader tells everybody what to do. Here, we have to be a bit careful about incentives, unlike in the previous case. So in general, if I'm not careful, okay, why do we have to be worried about incentives? Let's look at this person over here. This person over here has 2 neighbors. You can see my mouse, right? Yeah, or you can see where I'm pointing with my mouse? Yeah?
Yes.
Okay. So this person over here is going to have 2 neighbors inside their community and 3 neighbors in this neighboring community. Now, if L2, each leader only sends a message to the people inside their community. If this were a public message, if L2 would also send this message to this person, this would not work as an equilibrium anymore, because this person, if they learn that what community C2 does is going to be different than what C1 does, they want to do what C2 does, because they have 3 neighbors over there and only 2 neighbors inside C1. Right? But we're saved by the fact that messages are private. So this person here on the edge of C1 doesn't learn what these people are going to do. From their point of view, they're going to take each action with probability 1/2. So then, because they do know what their neighbors inside the community are going to do, they'd rather follow the recommendation of their leader. And you have that this is an equilibrium. Does this make sense? If you had public messages, you'd have to, this wouldn't work like this. Okay? And if you try to say, do this majority thing, let's imagine that each person sends out a recommendation, which is either +1 or -1, and each person, I don't know, does whatever the majority of the people in the ball of radius R say to do, or the people in their community say to do, you might still have an issue with incentives at the edges. I might want to do something different than this majority. But here, once you have private messages, the incentives are fine. Please ask any questions if anything is unclear. So how efficient is this? Well, along the white edges here, we have perfect coordination. These people are always inside each community. These people are always going to take the exact same action as their neighbors. Along the red edges, we only coordinate with probability 1/2, so we're going to have inefficiency. So the efficiency of this depends on how many red edges there are. How this partition into communities, does it include almost all the edges, or does it leave many, many edges cross-community, which is where you get inefficiencies. So this is going to depend on the graph and on our partition into communities. So let me show you one graph where it's very easy and you get very low inefficiency. This is just a line graph. So imagine a very, very long line graph. And what we're going to do, we're going to divide it. These communities are going to be segments of length 2r + 1. Why 2r + 1? Because then the person in the middle is exactly distance r to everybody in this community. So these cross-community edges, they only arrive once every 2r + 1 edges. So our inefficiency is going to be 1 over 2r + 1. In particular, when r is big, we have low inefficiency. Does this make sense? Okay. Here's another graph. Let's look at a two-dimensional grid. So think about a big two-dimensional grid. We're going to divide it into communities, which are going to be squares of edge length r. And inside, right, so the white edges are inside the community. The red edges are cross-community edges. The side length here is r. So inside, you'll have something like r squared edges. But the perimeter is only order r, maybe 4r or something. So you have a quadratic number of edges in R inside and only linear number inside. So inefficiency is again something like 1 over R. So here also, think of the graph as very big, but if we make R larger, if we coordinate with more people, we have better and better efficiency. The inefficiency goes to 0. So here's a definition. And this definition is supposed to capture when one of these leader equilibria works. So I'm going to say that a graph is epsilon r amenable. I'll explain this word amenable. It's a bit weird. If it can be partitioned into communities so that the radius of each community is at most r, and the number of cross-community edges is at most epsilon times the number of edges. So only an epsilon fraction of the edges are between communities. Okay, so this is going to be a geometric property of the graph. It means there is a good partition here into small communities. Good in the sense that there's only very few edges between the communities. Here's an equivalent formulation. This is the same as saying that there's a small this D is the cross-community edges. I have a graph. If I can find a subset of the edges that is small, it's only an epsilon fraction of the edges. And once I remove it, the connected components that are left have radius at most r. This is the same as being epsilon r amino. And this really is the same thing as having a good leader equilibrium, right? If I have a good leader equilibrium, the communities of that equilibrium will give me a partition. And if I have a partition like this, then I can use it to do a leader equilibrium. So this is what the next theorem says. I mean, I wrote theorem, but it's more like an observation. If a graph is epsilon r amenable, then there's an action symmetric leader equilibrium with radius of communication r and expected inefficiency at most epsilon.
So
Okay.
can I ask you one thing at this point?
Yes.
There is a concept that Steve Morris developed in his contagion paper that sounds a little bit like this: is cohesiveness or peak cohesiveness. Is there a connection at all?
Yeah, it's not exactly the same, but it's also not unrelated.
Okay.
Yes, it somehow captures a similar concept. Formally, I don't think it's exactly the same, but the spirit is really similar.
Yeah, because it has to do with intra-community versus extra-community
Exactly.
contact, no?
Exactly.
Yeah.
Exactly. So I wrote here the other direction is also true, but by the other direction, I mean, if you have a good leader equilibrium, right? So there exists an action symmetric leader equilibrium with radius communication r and expected inefficiency most of the time, if and only if the graph is amenable. It's just a rephrasing of the existence of a good leader equilibrium. Okay. However, I don't care in particular about leader equilibria. That was just like one simple way to do this. And Evan, suggested maybe a better path to doing these things. So these leader equilibria is just one construction. What I'm really interested in, on which graph is there some low inefficiency equilibrium, right? So can I do better than leader equilibria? That's just one example. So let me show you a graph where leader equilibria don't work. The graph is going to be a binary tree, so, right? I start with this person. They have two neighbors below them, and then each person is going to have two neighbors below them and one neighbor above them, and so on. So I'm going to have these levels. And if I look at everybody whose distance r from this person here, that's going to be these white nodes. At the bottom layer, there's going to be 2 to the power r nodes. But also the entire, this ball of radius r, let's make this a community. This entire community is just going to have twice as many people as 2 to the power r, right? And when you sum 1 plus 2 plus 4 and so on up to 2 to the power r, you just get 2 times 2 to the power r. So what we get here, if this is our community, half of the community is on the boundary. Right? So this is a community it's kind of bad. Half of the people in this community are on the boundary of the community, and they each have 2 edges going out. So in fact, the number of cross-community edges here is the same as the number of edges inside the community. That's a lot of cross-community edges. It's not some vanishing fraction of cross-community edges. So if this was your graph, choosing the first R levels as your community is a very bad idea. If you're going to do a leader equilibrium, this is a very bad community to choose. But it turns out that this is also the best community that you can choose on this graph. Any finite, so here's that combinatorial fact about this kind of tree. Any finite community that you take is going to have at least as many edges leaving it as it has inside it. You're not going to be able to create on a tree graph communities that have a small fraction of cross-community edges. Does this make sense? Which means that no leader equilibrium can have low inefficiency. I cannot divide this graph into communities of radius r with few cross-community edges. So leader equilibria really fail on this graph. Which is the same thing as saying this graph is not amenable. It's not epsilon r amenable for any epsilon less than 1. So the question is, maybe we can do something completely different here. Maybe let's do something with majority, and I don't know. There's a billion possible things that you could imagine doing. So far, so good? Okay. So the answer is you can't really do anything good on this graph. So this is our main result, and it says the following. If I have an action symmetric equilibrium with radius of communication r and average expected inefficiency epsilon, then the graph is amenable. not epsilon amenable, root 8 epsilon amenable. So this is sort of a partial converse to the previous theorem. The previous theorem said, if I'm amenable, I have a low inefficiency equilibrium. This says, if I have a low inefficiency equilibrium, then I'm amenable. The numbers are not exactly the same. Here's another way of thinking about this. Because amenability is the same as having a good leader equilibrium, what this says is, if any equilibrium can get me epsilon, then a leader equilibrium can get me root 8 epsilon, which is bigger than epsilon. Epsilon here, you want to think about it as a small number so that when you take root, it becomes bigger. But up to some quantitative difference, if the graph is not amenable, you cannot have a good equilibrium on it. Okay, so the message is this amenability condition is what determines whether or not we can coordinate on graphs. If we're amenable, we have a good equilibrium, this leader equilibrium. If we're not amenable, nothing works. Okay, so in particular, for example, on the tree that we saw before, no matter how big R is, you can coordinate very, very large distances, you're never going to have inefficiency better than 1/8 in any equilibrium. Okay. Now, there is a difference between epsilon and root 8 epsilon. So we have a necessary condition, a sufficient condition. They're not the same. There's a gap between them. We don't know where the truth is between this and that. It could be that the answer is really epsilon, that leader equilibria are always optimal, that there's never anything better than leader equilibrium. We don't know whether that's true or not. On cycle graphs, on things that look like a line, we know it is true. There, you cannot do better than a leader equilibrium. But we don't know in general for other graphs. Any thoughts or questions about this? Okay, so the plan for the rest of the talk, the way the time looks, is I'm going to explain the proof of this because I think that there are two nice ideas in this proof. One of them is even somewhat original. The other one is a really, really beautiful idea that's due to two computer scientists, Kleinberg and Tardosh. I've become a bit of an evangelist of this idea, so I'll explain it to you, and I'll explain. So I want to explain the main ideas in this proof, and that'll probably be all I have time for. Okay, I guess before that, sorry, I went ahead of what I want to say. Let me show you an even stronger theorem that we have, and it's almost the same statement. The only difference is that we have suppose that G admits an action-symmetric strategy profile with radius of communication R and average expected inefficiency epsilon, then G is amenable. So it's not about incentives. It's just information theoretically, physically impossible to coordinate well on non-amenable graphs. Okay, so what happens is when the graph is not amenable, it's not that there's no incentive compatible way of getting people to coordinate. Even if you prescribed what everybody does, these are now computers on the nodes of a computer network, and somebody wrote the software and it's trying to get them all to coordinate under this locality constraint and action symmetry constraint. On a non-amenable graph, there's no way to do this. So because it's more general, I want to rephrase this theorem in sort of probabilistic language. And the reason I want to do this is because this applies to many, many other models. It doesn't really matter what the incentives of the model are. Imagine that, well, we have some other model of interaction on networks. Maybe it's a repeated interaction. I see what my neighbors do. I send messages. I choose an action again and again. If at some point in time, what I have are actions that are local, so they only depend on things up to radius R for me, then the same theorem will apply. So I want to phrase it more generally. So here's a completely elementary probabilistic formulation of the theorem. I'm going to have a finite graph. I'm going to have independent random variables, Zi. You want in our model, these will correspond to the messages that people send, and beyond that, to any randomization that people perform, any mixing that people perform, that's all going to be captured in some Zi belonging to agent I. And these are independent random variables by the definition of a mixed Nash equilibrium. So I have these sources of randomness Zi at each node. And now I'm going to have what are actions at each node Xi. And I'm going to make three assumptions on them. One of them is localized. So each action Xi is a function of the randomness Zj, but only in the ball of radius r around I. So I start with randomness at each node, and now I calculate an action at each node that only depends on the randomness in the ball of radius r around that node. I'm going to normalize these x's. So now these are real random variables, but I'm going to ask that they have zero expectation and variance 1. And I'm going to assume that they're locally correlated. What does that mean? If I look at okay, let's look here. This is the mean squared error between I and j for neighbors ij on the graph. If I look at the average mean squared error across neighbors, it's less than epsilon. So this exactly corresponds to low inefficiency in our model, but just translated and made slightly more general to allow for real random variables. And the theorem says if I have this kind of process xi on my graph, these random variables in my graph, that locally they're very highly correlated, they're also local, each one of them is calculated locally, and they're normalized, then the graph has to be amenable. And I want to explain how to prove this theorem.
Can I ask something about
Yes.
condition 1? So the xi's, are they a deterministic function of the zj's? Or, so in other words, all the uncertainties in the zj's?
Correct.
Or are they not a deterministic function?
They're a deterministic function. They're measurable in the sigma
Okay.
algebra generated by the j's and the ball of radius r.
I guess you can have a zj's and xi's in such a way that, yeah, you could interpret it as a non-deterministic function, but you could always convert it into a deterministic function. Am I right? Or
Yeah, because you can throw into zi more random, right?
Yeah, exactly. So it's without lots of generality in a sense.
Yes.
Yeah, okay.
Okay, more questions? Okay, so let me tell you how to prove this. The proof is going to have two ideas. I'm going to tell you each idea one by one. They're going to seem unrelated and to each other, and then we'll put it all together. So here's the first idea. I want to start by just giving a quick overview of this idea of coupling. So what is coupling and total variation distance? I'm going to have some set omega, think of a finite set, and two probability measures on this set. A coupling of these two measures is a probability measure on the product set whose marginals are nu1 and nu2. And here's another way of thinking about it. I want to find two random variables, x1, x2, where x1 has distribution nu1, x2 has distribution nu2. Eta is the joint distribution of x1 and x2. So these are just all the joint distributions that have marginal nu1 and nu2. So that's a coupling, some way of putting these two distributions together in a probability space. And what we want to do is we want to find a coupling that minimizes the probability that these two are different. Okay, so for example, if nu1 and nu2 are the same distribution, then we can couple them in such a way that these two are exactly always equal, that the probability that they're equal is 1. How do we do that? We choose x1 from nu1, and then we set x2 to equal x1. Then it's also going to, if these two distributions are the same, then x2 will also have distribution nu2, which is equal to nu1. But when these two distributions are different from each other, we can't have these always be equal, because then they will have the same marginal distribution. But what you can hope for is when these distributions are similar to each other, we can get these two to be equal with high probability. We can get the probability that they're different to be small. So it turns out that the right way to think about this is with total variation distance. So the total variation distance between two probability measures is there's two ways to write it. Let's start with the one on the right. It's just the half the L1 distance. You calculate the mass that the probability that this nu 1 assigns to some point in my space, that nu 2 assigns to some outcome, and you take the absolute value, the difference of the absolute value, sum it up over everything. It turns out that this is the same as the following. I look at all events, all subsets, and I look at the difference between the probabilities that the two measures assign to these subsets. So if you think of a probability measure as a set function, so as a function that assigns a number to each set, this is just the sup norm. This is the most different probabilities that they can assign to any set. And sort of a theorem it's old, apparently it's due to Dublin from the 30s, is that the best coupling of nu 1 and nu 2 achieves that the probability that the two x1, x2 are different is exactly the total variations. Okay, so this is a very important concept, I guess, in probability and computer science. I've seen it used in economics, but I'm sort of explaining in detail because maybe it's not common knowledge for everybody. Here's a question that was asked by Kleinberg and Tardosh. It says, what if we want to couple more than two distributions? So I have maybe nu 1, nu 2, nu 3, and I want to find random variables x1, x2, x3 that have distributions nu 1, nu 2, nu 3. I want to couple them in such a way that pairwise, the probability that they're different is small. So obviously, I can't couple them so that pairwise, the probability that they're different is less than the total variation distance, because that's the best I can do without the constraint of the third one. But it turns out that I can always do this in a way where I lose a factor of 2. The probability that any pair is different is at most twice the total variation distance between their distributions. Does this make sense?
Yes, this makes sense. I think you just I just missed what I didn't understand completely what you wanted to say, but if I understand where you're trying to go with this, aren't you interested in xi different from xj, different from xl, ultimately?
No, because this is just going to be along edges. I want to look at the probability that the action there and the action there are different. So I'm only going to be interested in pairs.
Okay.
Does that make
Right.
sense?
You're not in, well, I
I
understand
don't
what
need
you just
everybody in
said,
the
but
graph.
the big,
I don't need
I'm missing
everybody
the
in the
big
graph to take the
picture.
same action. I'm just interested in pairs
Okay.
along.
So I'm asking because ultimately you want everybody who's within R to take the same action in some sense, right?
No, I just want people who are neighbors to take the same action,
Okay. All right. Okay.
right?
Okay.
Okay, so if I have 3 instead of 2, I lose a factor of 2. So now, what happens if I have 4 or 5 or 10? What I was expecting, you lose a factor of 4 or 5 or 10 or 2 to the power 10 or who knows what. But the amazing theorem is that it's always a factor of 2. So what they prove is you can take any collection of probability measures, and you can find an assignment of a random variable, one for each probability measure, so that pairwise, the probability that they're different is at most twice the total variation distance. You can take this collection to be uncountable. Take it to be all probability measures on your set. You can still do this. You always only lose a factor of 2. Okay, is the statement clear? Okay, so that's one idea. Now forget about it for a second. We're going to talk about a very different idea. I'm going to have independent random variable zi, and I'm going to calculate some random variable x as a function of these zi's. And a very natural question in statistics, maybe also in economics, is how much does each one of these zi's influence x? Right? So this is a question that statisticians have asked for a long time now. I don't know, since the 60s, 70s. They want to quantify how much influence does each input have on the output. Right? You can imagine maybe I'm trying to estimate something, And so the Z's are some independent draws from some distribution, and F is some estimator, and I'm trying to understand how much, well, okay, I guess Z's are different measurements of different things, and I'm trying to estimate how much is X affected by each one. Maybe I mean, this is also very natural in economics. I have some factors that cause something, and I want to know how much influence does each one of them actually have quantitatively. And specifically, the way I want to quantify influence is with a probability distribution over the input. So I want to assign weights that sum to 1, non-negative weights that sum to 1, that somehow capture how much influence each Zi has over this outcome F. So I want a probability distribution over the set of inputs. Does this make sense? Okay, so here's one way to do it. This is an idea, again, that came from statisticians, and it uses Shapley values. So I'm going to denote by phi I of V the Shapley values of a cooperative game V. I'm not going to define it now, but I hope you remember what this means. And now I'm going to define a cooperative game for this random variable X with these inputs Zi. The cooperative game is over the set of inputs. So the players in this cooperative game are the inputs. And if S is a coalition of inputs, Vx of S will somehow capture how much influence does this coalition of inputs have over the output X. Okay? And you do it by quadratic variation. With this is the variance of the expectation of X conditional on the Zi's in this set. So, for example, if this set is everything, if I condition X on all of the Zi's, well, the expectation of X conditioned on all the Zi's is just X itself. I know X if I know all the Zi's. So the variance will be very big, will be 1. It'll be the variance of X. If I condition on nothing, if I condition on the empty set, the expectation of X conditioned on nothing is just the expectation of X. This is a constant that has variance 0. So between that, what this captures is how much of the quadratic variation of X is explained by the Z's in this set S. So this gives me a number for each subset, and then what Shapley values do is they give me the influence of each particular one. So the way I'm going to quantify influence is the following. The influence that input I is going to have on this output X is the Shapley value of I in this cooperative game. This makes sense? Okay, so this is something that was proposed maybe 2014 by a statistician from Stanford. I'll have his name. It now evades me, but I'll have it in the references slide. But one contribution that we have is to prove something interesting about this, or mildly interesting. And here's what we proved. So I'm going to look at 2 different functions of the same inputs. And I'm going to calculate the Shapley influence of X and the Shapley influence of Y. So how much is X influenced by each input, and how much Y is influenced by each input, using these Shapley values. And I'm going to ask, when X and Y are very close to each other in terms of quadratic error, how close are these 2 distributions? And the answer is they're close. The total variation distance between these influence distributions is going to be at most sort of the L2 norm of the difference between X and Y. Here's another way of thinking about it. If you think of Y as a perturbation of X, what this says is, if we take this output X that somehow depends on all the inputs, and we change the output a little bit, we slightly change the function of how we calculate the output, the influence distribution only changes a little bit. And it changes a little bit in terms of total variation distance. So I'm almost, any questions about this? Okay, so given these 2 things, we're ready to prove our theorem. So just remember, what does our theorem says? The theorem says if I have these random variables xi that have high correlations for neighbors, then the graph is amenable. I want to construct a partition of the graph that has few cross-community edges. So this is what, let me actually go to the theorem statement back. The theorem statement says if I have these xi's that are local, they're normalized, and they have high correlations across neighboring edges, the expected difference between neighbors is very small, then the graph is amenable. That is, there's a good partition. So this is what we have to do. We have to, given xi's with high correlations for neighbors, we want to construct a partition of the graph that has few cross-community edges, a partition with small radius r communities that has few cross-community edges. So here's how we're going to do it. We're going to calculate this Shapley influence distribution for each agent. This is mu xi. And each agent is going to choose at random a leader from this influence distribution. Now, we have this contraction or this Lipschitz property, which was the previous slide. It says that if these influence distributions, it says that if these x's are similar to each other, then the influence distributions are going to be close. So if these x's, the difference squared between neighboring x's is epsilon, then these influence distributions are going to be, the total variation distance will be at most epsilon. So I said that each agent I is going to choose a leader, but they're not going to choose these leaders independently. We're going to couple their choices. We're going to use this grand coupling to couple their choices, which means that neighbors are going to choose, are rarely going to choose different leaders. So what's going on here? Somebody gives us an equilibrium in which agents who are neighbors are likely to choose the same action. What am I going to do? I'm going to imagine now that each person chooses a leader. They're going to choose as a leader somebody who influences them a lot. So they're going to choose their leader at random from this influence distribution, from the distribution which gives high weight to those whose messages influence me a lot. And we're going to couple these choices so that neighbors are likely to choose the same leader. Why can we do this? Because neighbors are going to have similar influence distributions. Now we're going to have communities. Communities are formed by agents who have the same leader. Everybody who chose Evan as leader is going to be one community. Everybody who chose me as leader is going to have a different community. And we're going to have few cross-community edges. These are exactly the cross-community edges, the edges where neighbors chose different leaders. But the probability that every particular edge is a cross-community edge is very small. So on average, we're going to have few cross-community edges. And then we have that the graph is amenable. Okay, so I'm pretty much done. I have a minute left. In economics, people have looked at these coordination games. Maybe these are the earliest references I can find. Maybe Ellison is the first. This was the sort of statistical mechanics way. It was pretty mechanical. People were updating based on what their neighbors did, sort of at random, maybe more likely to match than to mismatch. And what Ellison looked at is what happens after a long time. So you coordinate locally, but you wait a long, long time, which means that this coordination can spread. We're doing something different. We're forcing it to stay local. We're not looking what happens after a long, long time when information has traveled from one side of the graph to the other. We're asking what happens when it stays local. Morris also, I guess, goes along a similar route. And again, the question is what happens after a long time. Interestingly, like somebody pointed out here, I forget who was, a kind of a similar in spirit condition comes up. There's slightly less related works, including by people here. I don't have time to explain all of them. People in math have looked at this concept of an amenable graph. It started with von Neumann, who introduced this idea of amenability in a slightly different condition. But people in math are also interested in this. This is where this word amenability came from. So Sobel, I think, is the first person in statistics that I saw that introduced this idea of these influence distributions. Owen introduced this using Shapley values to calculate these things. That's all I have. You can read the conclusion, but there's no new content here. So thank you very much.
Thank you, Omer. Thank you for this wonderful presentation. So now we're gonna open all the floor for questions. So I'm going to start with the panelists. So just following alphabetical order. So Antonio, do you want to start?
Yeah, I think particularly the set of tools that you have here is very interesting, and it's true that the conditions seems similar to what Morris did, but the approach is very different because you're taking these correlations. It doesn't do anything like this, so it really is very different. It's sort of it has to be somewhat similar because there's this connection between intra-community and inter-community links, but the approach is so different that I think it will be useful to people. So I think to me, that seems the major contribution. Now, moving on to something slightly different and in the realm of speculation mostly, something that comes to mind is sometimes people have incentives to coordinate locally, but in fact, they want to diverge globally. Like, young people say some kind of word to communicate between one another, and they really want this word to not be the same that their parents use, and that's kind of important to them. So this is a different kind of world in which you want coordination to really stay local and you don't want it to go global. And then I mean, this is too off the hat here, but you have a sense that the tools could be useful to understand phenomena like this?
That's a good question. So maybe there's some edges along which I want to miscoordinate and some edges where I want
That's
to
right.
coordinate.
Yeah. Yeah.
That's a good question. No, but maybe that's a good idea for the next paper. I like it. I'm not
Good.
sure. I'd have to think about it. Yeah.
Yeah, I imagine this is too far off, but I think it's important because it's true that this literature has tended to focus on coordination, like global coordination, but there are many social phenomena in which the coordination, in a sense, wants to stay local. In some cases, it's not necessarily that you want to stay local, but in some sense, the actual action that you use has a value for the community, and you don't want to move to the other's community. I mean, if the other community comes to you, fine, but you don't want that's a slightly different story. But there's many more angles to this problem that
Kind
differ
of
from the ones that have been studied, at least in the econ literature. And I would be interested in knowing about more of this. And I think the tools probably can be used.
I think it might be interesting to try to think of a model of cults. So if I'm running a cult, I want to have my cult to have sort of few edges out to going outside the cult, right? But initially, when I'm growing my cult, I do want to have a lot of edges going outside so that I can bring in more people. So there's some tension between wanting to have an insular community, but then if you're too insular, then your cult has 3 people and never becomes big. But if you want to have a cult of 1 million people, how do you create something like Scientology? You needed to, I apologize for any Scientologists in the audience, but you needed to somehow have a large surface so that it can recruit more people, but you also don't want it to, you want people to be isolated so they don't hear that they're insane.
Thank you. So, yes.
I'll be happy to jump in.
Yep.
I had sort of a different type of question. I'm trying to think about this, property of amenability, and of course, I can look at it and I understand the mathematical definition, but if I try to think about like, okay, how am I going to check whether a given graph is amenable or not? And the first thing that strikes me is that this looks like it's the kind of thing that is likely computationally hard, and I'm wondering, are the like I'm also just I'm generally wondering, one, like how easy is it to check? Two, are there like natural, like interpretable conditions that would tell me a graph is amenable or not? Or are there like, you know, well-known classes of random graphs that are going to generate an amenable network with high probability? Or are they going to be non-amenable with high probability? I'm sort of, you know, broadly interested in, you know, how do I tell, when a network is amenable?
That's a good question. I don't know that people have studied this computational question. That's a nice question about how to calculate this. About random graphs, so Erdős-Renyi graphs, if you take Erdős-Renyi graphs with, say, constant expected degree, it's going to locally look like a tree, and it's not going to be amenable. So that's one way to construct finite non-amenable graphs. But obviously you could have different models of a random graph that
I'm building on that though, like one just sort of like immediate thought that comes to mind is, there's a simple adjustment of the Erdős-Renyi model where, okay, I'm also going to like add some clustering by randomly creating links between second degree neighbors with some independent probability after I generate the Erdős-Renyi graph. Would like adding that clustering create amenability, or is it still sort
No,
of
it's
too
it's sort of
expansive?
yeah, it's sort of it's a rough geometry kind of property. It might change the constants, but it's not going to change the essence. On on infinite graphs, yeah, maybe this is beyond, we can chat about this in some other. On infinite graphs, there's a really nice character. So on infinite, the original concept of amenability was defined for infinite graphs, and it just means that as you take r to infinity, the epsilon goes to zero. So an infinite graph, a graph is amenable if I can find sets with arbitrarily small surface to volume ratio. So if I can find communities that have arbitrarily small fraction of edges leaving the community as compared to the edges inside the community. And that turns out to have a really nice economic sort of a really nice equivalent definition, which is the following. Imagine that you have an infinite graph like this, and you give each person $1, and you try to find, you allow each person to send, you don't give each person $1. Each person can send up to $1 to each one of their neighbors. Okay, so, and you allow a central planner to figure out how to do this, they tell each person how to send at most $1 to each one of their neighbors. And the question is, can you do this in a way that everybody becomes 1 cent richer? Right? So on a finite graph, this is impossible. There's conservation of money. We're just passing money from one to the other. How can we become all 1 cent richer, right? It's impossible. On an infinite graph, well, if you do this on an infinite tree, what you can do is have each person pass $1 up. So now I give $1 up to my parent, but I have 2 children. So actually everybody becomes a whole dollar richer. We've created money out of nothing. It's like a Ponzi scheme. And the theorem is, on an infinite graph, you have a Ponzi scheme if and only if the graph is non-amenable. On amenable graphs, on say z squared on a 2-dimensional grid, there's no way to send money. There's no money exchange scheme like this that makes everybody 1/1,000,000th of a cent cheaper even. But on a tree, you can get everybody to make more. So, and the proof of this is sort of a max cut min flow. It's a linear program. So it might be that amenability boils down to solving some linear program. So now that I think of it, my guess would be that on a finite graph, you can write a linear program, and the optimum would give you this epsilon in the amenability. It's not going to be very nice, but at least maybe it's computation.
Thank you. Any question from the audience? So I have a question. So, I mean, to what extent can I interpret R as rounds of communication?
Good.
Because
So
it
yeah,
seems, I mean, rounds of communication open the door to a more sophisticated strategic interaction, but it seems that that's irrelevant for your result.
correct. Okay,
So,
excellent question. I should explain this myself better. Yes. So yeah, if you know, you can, let's imagine a different model where people can only communicate with the people they're directly connected to, and you can communicate with for our rounds. So that allows people to pass messages along, and maybe we can hope to coordinate like that. And if we do it for our rounds, in the end, information only travels up to distance r. So the main theorem again applies to this model, which is why I phrased it generally like this, because again, actions are these random variables that only depend on the randomness up to distance r. So if the graph is non-amenable, we're not going to be able to coordinate like this.
yeah. Okay, understood. Thank you.
You could imagine, you can imagine a model without communication. I just take an action in each period and observe the actions of my neighbors. Again, information up to period r will only travel distance r. So you can ask, what is it that people do at time r? You're going to get the same answer. It cannot be well coordinated.
Thank you. Any other question?
I do, but should we stop recording given the time, or I can ask a question with or without recording? So I don't.
Well, okay. I mean, we can stop the recording. I mean,